You guys, quiet down. Any questions on the homework? Guys, quiet, please. So, obviously I didn't sign 110 or 150, 150. I signed these two middle ones here and all these problems here. The answer key, I think I posted this school G. I should have. Actually, here's the answer key right now. So for number 32, you just have to find the derivative as well as 42. 42, you could use the quotient rule. Any questions on that so far? And 32, by the way, switch those radicals to fraction exponents. So make it 2 times x 1/2 power, or minus 1 times x and negative 1/2 power, or just minus x and negative 1/2 power. And 42, you have that right there. Just plug in 2 and 1 to find the slope of the tangent line. Then when you write the equation of tangent, please put in point slope form. That makes it easier. 44, that's just verifying the constant multiple rule, like the product rule. It works, right? So not hard, right? 46 is right there. 47 is right there. There's 49 and 56. Any questions at all? No? You guys are fine?
No, can you explain the explanation for 49?
Sure. Okay, let's look at 49. Well, I'll see if I can explain it. Okay. Recall that the area of a circle is that, and circumference that. Notice that dA over dr equals the circumference, right? Okay, guys, quiet, please. Explain in terms of geometry why the instantaneous rate change the area with respect to the radius should equal yeah, that is a good question. Why is that? I mean, I know from a calculus perspective it makes sense, but in terms of geometry, let's look at what the solution says. Okay, guys, quiet. So if we increase R, I see, by a small amount delta R, then expected change increase will be 2 pi r times delta R, which is shown in the blue area. Okay, so I see. If you have like this little, right? Think like a ring. And so right now, let's say the original circle from here to the inner radius, the inner part. And if you expand it, might as well call it delta R, the change in the radius. Now you're getting the radius a little bigger, right? What's happening is that right now the circumference is 2 pi r, but what's going to happen is that you're going to take that and multiply it by delta R. So the change and increase in the area will be that, because what you're doing is you're essentially you're like, what if you like cut the ring? Like, or let's say it's a piece of paper, that might be another way to cut the ring, but what if you take a piece of paper and expand it as a rectangle? What will be linked to that rectangle? The circle distance, which is 2 pi r. And what's the width? Delta R. So the area changes by that much. That's why. Because again, if you were to cut this and like straighten it out, you have a rectangle with a length of 2 pi r and a base of or width of delta R. So that's how the area changes. And that's what really a derivative is in the first place. It's all about the change, right? The change in in this case, we're doing the derivative area. It's a change in area with respect to the area. So it's kind of like a change in area over a change in R. So then we do 2 pi r of R. Sorry, 2 pi r times delta R over delta R. When you do this, so the change in area is 2 pi r times delta R, and the change in R is delta R as well. Those cancel, and that's why you get 2 pi r. But again, it's like you took this and expanded it like this. Well, that's 2 pi r this way, and that's delta R this way. So the area of this, the change in area is all that right there. Okay, that's why. Yeah, that makes sense. Yeah, I didn't think of that way, but it's kind of cool. Yeah, okay. I was going to give a total BS answer if I didn't look at the answer keys. So just be honest. All right. Next up is these pages 137 to 142, 1, 2, 5, 8, 9, 19. For 5B, is to use the secant slopes approximate the velocities. So yeah. Any questions on those at all? It's kind of like what we did talk about on Friday, but we didn't get to finish those notes. We're going to finish those today and then try to do 3, 5 today. So no, we're okay. All's good. All right. That's easy. No questions? Okay, and then let me just so I pace myself properly for today. 4-1 is 5P. Okay, so here's my plan, guys. The notes for 3-5 is really short. It's on trig. And I'm not sure if I'm actually even do the formal proof. We could try maybe. I could play around with it a little bit. We could try the formal proof for the derivative trig functions. But we do need to finish 3-4. So we'll do that. We'll do 3-5. Wednesday we'll do 4-1. After 4-1, no more new material. So the hope is after Wednesday, we have no more new material for the rest of the year. And the plan is to do 2 full days review for this upcoming test, which is on the 15th. So I moved it to the 15th, I believe. Is that correct? Yep. Yeah, because that way I'm testing for all my class, well, all my my Algebra 2 class in this class. So for most of my classes, I'm testing. So that's kind of the story there. Looking at the calendar really quickly. So the final is actually 3 weeks from tomorrow. So it's coming up pretty fast. So coming up really fast. Basically 22 days from now. So yeah, so we'll do 4-1 on Wednesday. We'll do review for the tests on Friday, as well as more review on Monday. Tests will be on Wednesday. 4 full days of final exam review, and a final exam on the Tuesday. And there seems to be a discrepancy here, because I think like in the newsletter and other communication, it says that the math final is in the afternoon, but this calendar says in the morning. So let me get some clarity on that from my department chair. Is he thinks after? You're probably right. Probably is. So this needs to be updated. It's yeah. So anyway, hold on. I just gotta check this with Spout. Okay. Yes. Go ahead.
Did you say you're testing on Wednesday?
Yes. Correct. Then we'll test a different day. Yeah. Yeah. We'll talk offline. Totally. 100%.
Mr. E?
Yeah.
I think I have the UP exams on our set slot.
What JP?
Comp sci principles.
Okay, that's fine. Actually, let me pull that up right now. Ryan, do you have the same one, AP Comp Sci Principles?
I have AP World.
AP World, got it. Yeah, 15th is yeah, World and Comp Sci Principles, Music Theory and French Language. So yeah, if you have a conflict, not a big deal, because we're just doing review for finals after that. So it's totally actually, I mean, we're done with the new material by Wednesday, and we're reviewing on Friday. So if you want to take it even earlier, you can too. It's up to you. Whatever you're comfortable with. Or you do it afterwards. You do it like the Thursday or Friday. It's fine. Totally flexible. Okay. Anyway, guys, let's keep moving. Let's go through the notes here. All right. You guys quiet. And I do probably need a calculator. So let me pull up my graphing calculator. Give me 1 sec. All right, here we go, guys. Okay, guys, quiet. Guys, we're doing the notes. Thank you. All right. So anyway, you got a rocket here. It's down for page 5 of the 3.4 notes. It has a launch velocity, initial launch velocity of 360 feet per second. And the model is this right here. It's modeled by this equation. So you can actually factor out -16, right? And a t. So you should get t minus 6. Sorry, t minus 10. Okay. So you have 0 and 10. Okay. And how high does it go? So it's going to do something kind of like this, right? Does that make sense? So I don't really need to use calculus here. I can just kind of figure it out, right? It's not that hard. What do you think the height's going to be? I get 400, right? So you could have used, by the way, you could have used calculus if you wanted to. What's the derivative of this function, by the way? And then when you're at the high point, what's the slope of the tangent line when you're at the high point? What do you think that slope is, that tangent line? 0. So we're not going to quite do this kind of stuff in this class. It's kind of bummed because I love optimization. Those are cool problems. You'll have to do that in the fall, your next class. But see how I get that? T equals 5. So that's another way you can use calculus too. This is why I think calculus is so cool, because it really helps you to get a more accurate feel on what's happening with highs and lows or extrema. But honestly, find the vertex is what we needed, right? And I found the vertex by using symmetry. And how to use symmetry? Because I knew both x-intercepts. How do you both x-intercepts? Because I factored. This is like an algebra 2 type problem, really, more than anything else. Maybe even algebra 1. But calculus confirms it, right? Calculus totally confirms what we're looking for. So part A, I think I kind of beat that one to death. So we're good there. Did that make sense? 400 feet is the high point. At 5 seconds. All's good. Okay. Now, what is the velocity and speed of the rocket when it's 336 feet above the launch pad on the way up and then on the way down? And it said velocity, not speed. So 336, we'll say 336 is right here. So if I drew that tangent line, right? What's the slope of that tangent line? The first one, is that positive or negative slope? And it should be positive because it's going up. How about this one here? Should be negative because it's going down. Because you're losing distance, or you're losing a position, right? Because we're measuring it as a position off the ground. So it's getting closer to the ground on the second tangent line, right? The first tangent line's going up. Okay. Well, I have my derivative, right? But before I even do that, I don't know what the time is, right? I'll call this T1. I'll call this T2. So I got to first figure out, let me erase this for now because it's getting a little distracting. Okay. So let's set the equation equal to 336 and solve for T. So you can actually do this, right? Does that make sense? And I think I could actually factor out a 16. You actually can. I was gonna use quad form of a calculator. Is that 21? Okay, so this actually worked out really nicely. We're okay with that? Kind of makes sense, right? So happens that T1 will be 3 and T2 will be 7. Okay. And if I want to find the velocity, that's easy. S prime of 3 and S prime of 7. And what was S prime of T again? Right. So, that's messy. Let's try it again. Okay. There you go. So makes sense, right? We're good. And then when does the rocket hit the ground? I mean, that's pretty obvious at 10 seconds. So yeah, so pretty easy stuff, right? Not too hard. Just
You would say one, like 164 and negative 64, and then for
Correct.
speed, you would say
Yeah, of course, right, 100%. Right. All right. Yeah, go ahead.
If it asks for the acceleration, would all we have to do is make it the double derivative?
Yeah, and this negative 32, which is actually true for acceleration due to gravity, it's about negative 32 feet per second squared. I think that is true. So yeah.
Well, then, isn't it accelerating? Oh, wait, no, it's
Well, no,
decelerating the entire time.
of course, yeah.
Okay.
Because that's just acceleration due to gravity. That's just a physics thing. You can also do parametric equations. We have talked about parametric equations in this class, but I'm not going to really care about it for this particular unit. We're just going to keep it all in rectangular coordinates. But yeah, I mean, we could see that. Yeah, I'm not going to worry about that. Let's just move on. Okay, let's go to example 5. Now, this is all. Another thing we need to talk about too is marginal cost and marginal revenue. So let me show you my filled out notes on this stuff, and then we'll have a discussion on it. Thought I filled out notes on this. Okay, that's fine. I'll just do it right here. Okay, so guys, here we go. So let's say you're making some product, and the product is called Action Math Man Figures. Kind of lame, but just go with it. I know Pan likes it. Okay. So the cost function is that, okay? Well, what are the units of the derivative? So x is the figures. So f prime of x is going to be the change in cost over the change in figures. Or the cost per figure. So what it really means, I'll put as a text box, the change in the cost of one figure when producing X figures. So for example, what if I want to find F times of hundreds? So it means you're making 100 figures. So it's going to be the change of making that 100 figure or making, or the increase of producing one extra figure when you make 100 figures. Now, if you think about it, when you have a business, there's lots of costs, right? There's a cost for, the rent, for the utilities, for the employees, for the materials, maybe renting the equipment or whatever. So if you're making a lot of figures, will the cost per item go up or down as you make more? What do you guys think?
Probably goes down.
Goes down. And why is that? Yeah, but also like a lot of the costs you have are fixed, right? But the thing is that those costs get diluted as you make more product, right? As you make more product, there's get like, for example, let's say it costs $10,000 to rent the space. So you're stuck with that cost, regardless if you make 1,000 or nothing. Now, if you make more, obviously you got to pay the employees more hours, more materials, but ultimately those costs become less as time passes. So if you look at part B, so this is like a business calculus question, but if you look at part B, what this means is that the cost of making one more figure after producing 5,000 figures is 14 cents. That's how you interpret that. Because you made 5,000 figures, right? That's X. But this is a slope. This is a rate. It's what is a rate of cost per figure. So to make one more figure after 5,000, so you figure, okay, we made all this much, well, okay, well, you gotta make one more. What's it gonna cost us? Or let's say you want to make like 10 or 20 more, then on average, you figure, yeah, it's gonna cost about 14 cents, roughly. So which value do you think is bigger? Definitely this one's bigger. Kathy, a question, go ahead. No, at a specific moment. Because remember, there is an instantaneous rate of change at that specific moment when you produce 5,000 figures. So that probably tend to be bigger, and that's mainly because the fixed costs are more impactful but they tend to go down as time passes. So in this case, sometimes we have to do respect to time. Hold on. In the same way, we've given a special name for the derivative with respect to time, which is ds over dt. We do the same thing for costs, or we call like a marginal cost or marginal revenue. So on margin, like, okay, how much it's going to cost to make an extra thing, or how much more extra money we're going to make. Okay. Let's talk about a table problem, because table problems are very popular on the AP exam, or AP Calculus AB. Let me zoom out just a tad. Okay. So what do we got here? You're comparing days and temperature, right? Guys, quiet, please. And you're looking at a pond. So we're doing this over every 3 days or a 15-day period, right? Okay. So for the first 3 days, we go from 20 to 31, and we just see this increase. And we can look at it graphically as well. Graphically looks like that. So you have to find W prime at 12. I think we already kind of talked about this. Like, how would you approximate? Right. You want to really focus on these 2 points here. And so, yeah, it's W15. Which is 21 minus 24. Or no, 1/2 degrees Celsius per day. That's all. Pretty simple, right? And do we have to really graph it? No. But we did. We felt like it. Because you figure the secant line is going to be pretty close to the tangent line at 12, right? They're going to be pretty darn close. Does that make sense? And I think we did something like that earlier, so I think that's fine. And then for example 7, and then we're going to move on to the next set of notes. Yeah, same thing. R prime 45. So let's focus on these two here. So R prime 45 will be approximately R50 minus R40 so 55 minus 40 so you get 1.5 and what are the units? Per minute squared. So it's kind of like acceleration for volume, if that makes sense. You're looking at the rate of change of the flow rate. That makes sense, or rate of so it's a rate of change of a rate of change. It's like a second derivative in a way. What we're doing here, but do you need a graph? No, graph is not necessary. But it's 1.5 gallons per minute squared. So those should be pretty straightforward. Should be really, really simple. Okay, we're good on that. And then the homework, just to make sure that actually I think we may have had homework on that already. Homework files. We did, yeah, that's why I look familiar. Okay. Yeah, because next homework's going to be still going back to 137, 142, 126, 128. Yeah, there's some other stuff here, 147, 149. So yeah, anyway. I'll make sure you guys get work on that. All right, let's keep moving here. All right, here we go, guys. Now let's move on to trig. These notes should go pretty fast. So I'm just gonna kind of tell you these formulas right now, and then we're gonna understand why they work in just a little bit. Okay, the derivative sign is cosine. The derivative cosine is negative sign. This has to be in radian mode. I'll explain when we do the derivation of the proof, or the proof of why these work in just a little bit. But it had to be in radian mode. By the way, we rarely ever use degrees in calculus. I actually don't even know if we even use degrees at all. So make sure you're in radian mode, because otherwise you're going to really mess things up. So very important. Make sure you're in radian mode. That is a default anyway. And again, when you go through the formal proof of these derivatives, the assumption is that you're in radian mode. Now, graphically speaking, just so you can see why this makes sense, and we talked about this, I think, last week. I think Oliver may have brought this up with someone else. But this is sine. It wasn't. Yeah. So this is sine, right? So right now, the tangent lines are positive, right? Positive slope, and then it gets to 0 over here. Well, pi over 2, cosine pi over 2 is 0. But before you get pi over 2, cosine is positive. Then from pi to pi, slope to the tangent lines are negative. Cosine is negative in the second quadrant. And then by the time you get to 3 pi over 2, it's back to 0 again. And it gets back to being positive in the fourth quadrant. So it kind of makes sense, right? Now for cosine x, it's negative sine x. So you could just kind of think of it from a graphical perspective, right? Like right now the slope is 0, but then the slopes are negative, but you counteract that by doing the negative out in front, right? Because sine is supposed to be positive anyway in the first. Well, actually, sorry, let me take it back. Sine is positive in the first quadrant, but because you have a negative, that creates a negative. Because you have negative tangent lines, that's why you have negative sine x. That because you need to have that negative afterwards. Again, it's cos x. And then you hit 0 over here. Well, when you get to pi, right? This cosine pi is -1, sine pi is 0. Then it gets back to being positive. You get these positive slopes afterwards. And that's sorry, let me take it back. No, yeah, no, sorry, I'm just totally confused myself. But yeah, you have these negative tangent lines. The sine's positive in that quadrant. Okay, that makes sense. Then it's negative afterwards. There we go. That makes sense. You have the negative to counteract it. I think what I meant to do. Is this. That's what I meant to do. Anyway, that's what we got. Now tangent x. Now, do you guys remember the identity for tangents? Sine over cosine, very good. And what derivative rule can I use here? Quotient rule. So you do low d high. And real sine. Okay, you got it. All right, good. Minus high d low. Over low squared. And away we go. So the negative sine x is derivative cosine. So you wind up getting cosine squared x plus sine squared x over cosine squared x. There we go. Right? Now, next up, for cotangent x, that's cosine over sine x. So if you do that one, that should be low d high. Minus high d low. Over low squared. But you wind up getting negative sine squared x minus cosine squared x. What does that top become? Yeah, previously got positive when we had sine squared plus cosine squared, but yeah, you get -1. So it becomes negative cosecant squared x. So you can just derive all these, right? They're pretty simple. As long as you know your identities and know your derivative techniques, you're fine. Here you could do a quotient rule. So low d high minus high d low. Wait. That's 0, my bad. Minus high D low over low squared. So what do you get for that one? You get sine x and what's sine over cosine? And what's more of a cosine? So it becomes tan x secant x. And lastly, for this one, that's more of a sine x, right? So low D high minus high D low over low squared. So it's negative cos x over sine x times. So it's negative cotangent x times cosecant x. We're okay with that? No, you're multiplying. Doesn't matter. So those are all the derivative of trig functions. So the problems are pretty straightforward. So we're gonna be done with these notes pretty quickly, and we'll do the formal proofs after that. But yeah, this is pretty easy, right? Like, okay. Actually, I'll just show you the answers. It's pretty. We'll just kind of talk it out. Yeah, I mean, if you think about here, it's kind of small print. Yeah, I mean, that's pretty straightforward, right? Like, that's product rule. So x cos x plus sine x times 1. And that's just negative sine x. So we already talked about that. We already saw graph what's happening there. We didn't do a formal proof for sine cosine yet. We will eventually. But yeah, if x cos x, that's sine x, negative sine goes away. You said that, right? Won't be pretty straightforward. It's not that hard. Example 2. You're asked to find the equation of the normal line. Let me adjust this a tad. Remember, normal is perpendicular to a tangent line. Tangent line is a derivative. The derivative we know, right, is negative cosine squared x. So great, plug in pi over 4. You get sine pi over 4 is root 2 over 2, but you got to flip it. Well, you got to square it first, which is 1/2. Flip it, becomes negative 2. But because it's a normal line, you got to do the negative reciprocal, which is back to 1/2, right? Yeah, and just putting pi over 4 and 1 because sine cotangent pi over 4 is 1. You're doing point slope form, so again, pretty straightforward stuff, right? Again, identify the y coordinate when you use x plus pi over 4. You guys know that unit circle. That many year times now. It's pretty good there. So always spend all this time in trig, right? Because it can't be an issue anymore. Take derivative. We know that we just derived it earlier. Plugging pi over 4 into that, you should get negative 2. But since you want a normal line, it's a negative reciprocal, so it's positive 1/2. Boom, boom, boom. We're good, right? Easy peasy. The normal line is perpendicular to the tangent line, always. Yeah. So you have a curve, you have a tangent line that just grazes it. The normal line is perpendicular to that at that point of tangency, or a point of normalcy, if you want to call it that too. Okay, then here, that's just a quotient rule. Easy peasy again. You have cos x over 1 minus sine x, so take the derivative, not that hard. Just do it. There you go. Remember low D high, so derivative cosine negative sine. Cosine, derivative 1 minus sine x is negative cosine x. Boom, boom, boom. Work it out. You should get sine squared plus cosine squared, which is 1. We know this. And then do some fancy factoring. Or whatever, not factoring, just simplification. So, also have to be mindful that like maybe if there's like multiple choice question on an AP exam that you want to match with one of the choices, so you got to be comfortable with your identities. So the identities do kind of come back. They don't make the identities too tricky though. I've never seen like double angle or like half angle formulas. Like it's usually Pythagorean trig identities or maybe tangent, sine, or cosine. Maybe the other variations of the Pythagorean trig identity, like the one the secant or cosecant, which you can always derive by dividing both sides by sine or cosine or sine squared and cosine squared. The Pythagorean trig identity that's sine squared plus cosine squared x equals 1. But yeah, pretty straightforward. And obviously you should know your reciprocal trig functions as well, like cosecant, secant, cotan. But that's really it. You don't really I don't think you really need to know like the even odd identities. I don't think, or the cofunction. I don't think those really play a role in the AP exam. So keep it pretty simple. Okay, we're good. Okay, cool. So let's talk about the formal proof of the derivative of sine x and cos x. Now, you guys might remember when we did this limit here, that limit was 1. So it means that this would also be 1. And this one here, I think it's 1 also. Let me double check. I'm not 100% sure. If I do like cosine of 0.001 minus 1 divided by, okay, so it's probably going to be 0. Is that right? Guess so. Let me look that up really fast. Okay, it says 10's a 0. Yeah, I'm a little rusty at that one. Yeah, okay, there we go. So 0. Okay, great. We'll just assume that. So anyhow, if you work this out, you're gonna have to use a sum. Now, again, they don't ask this on the AP exam. This is just for us to understand why the sine is cosine. But if you use the sum formula or sum or difference formula, whatever you want to call it, so you got the limit as h approaches 0 of sine x cos h plus cos x sine h minus sine x.
The second thing, say, then they go sign at H.
Cos H.
I'll do it again.
Yeah.
Sorry, my bad. No, my bad, my bad. Any more space? Brian, go ahead.
I'm looking. Like if we were more time pushed, you would have to do this, right?
I'm not asking you to do it. I'm just showing you, just for showing you. That's all. It's not a test question. So in this case, if you plug in 0 for h, you get sine x. Yeah, 0 for h. Give me a sec here. Yeah, you get 0. So sorry, hold on a sec. You're right, it's 1. My bad. My bad. You're right, it's 1. You're right, you're right. So what happens? These cancel, right? So what are you stuck with? Cool questions so far? Questions? You have a question? Okay. If you keep going, but hold on, no, guys, no, guys, don't do that just yet. Just watch what I'm doing. What's the limit of sine h over h when h is approaching 0? So you just get cos x.
Uh,
That's why it's cos x. That's why it's cos x.
why, like, that makes sense. But how do you know to plug in 0 for the only the cos h and not for the sine?
Just do. Just do. Yeah. Yeah, because if you do, obviously then everything goes away. You get 0, 0. Yeah, I'm gonna do the next one. Yeah, go ahead.
This is why, sine H and H, equivalent, like they could be like different.
They get pretty close. It's the same thing when h is approaching 0.
Because sine X starts with a slope of 1, so then.
I don't know, actually. I'm not sure. But I mean, numerically, they're pretty much identical. So, Oliver, go ahead.
So you can do partial substitution like that, like you only.
Right.
plug in-
Yep. 100%. Yeah. So same thing here. Guys, quiet, please. So you have cos x times cos h then I'm gonna be selective here again. If I plug in 0 for h, I get cosine x minus sine x. Yeah, you guys get the idea. We're gonna be selective with what we plug in. That's a better way of putting it. Those cancel.
It's the same thing.
And then you have negative sine x and these just go away.
Sine of H.
You get that.
is 0 though?
No, sine h over h is 1 when the limit of h is approaching 0.
This sine of 0 is.
Well, sine of like a small number, like sine of 0.001 is basically 0.001. Sine x and x are pretty much similar. Small x. They're pretty much the same. Right, pretty much, right, exactly. And actually, Ari, were you saying something about like sine x and x like looking the same, like graphically, or?
I was saying that because like the slope.
Yeah, actually, you are correct. That's called local linearity, which we don't talk about until next year. So, like the sine graph looks like this, right? So in the beginning, it's pretty much like y equals x. Yeah, I mean that's the way of thinking about it, sure. And then lastly, I'm just gonna show you the filled out part. Just know your unit circle, know the basics. They don't really expect you to know too much from unit circle. I mean, again, AP's on your radar until next year for this class. But just know some of the basics of trig. So anyway, your basics of unit circle. And that's pretty much it. So I knew I was going to finish these notes pretty fast. So homework will be some pages from the textbook, which I'll update right now in Schoology. But you guys should know your unit circle, so I'm not too worried about it. I'll just freeze the screen.